Okay, SACE 2018 exam. Now, you might be interested to know, this is probably my favourite exam out of the ones that are out there. 2018 exam, so you'll hear me say that a bit. And this is a beautiful question. So we have a curve here, and we're told the equation of the function. Now what we're going to be doing here is recollecting a bit of calculus. It's a good opportunity for us to bring it back in because we are going to need it for the rest of the unit. So we have considered a function, the graph is shown alongside here. I'm going to draw an approximation of it. And it goes like this. Okay. An estimate is required for the area of the function between x is 1 and x is 3. Alright, that's part A. Part I. An overestimate of the area is to be calculated. Using 4 rectangles of equal width, draw the 4 rectangles used to obtain this estimate. So we want to draw 4 rectangles between x is 1 and x is 3, and they are an overestimate. So overestimate means upper rectangles. Okay, so if you can get those on there now, that'd be good.
Do you have tennis in everything?
Okay, so if we've got 4 upper rectangles, alright, so 1, here's 2, so 4 upper rectangles, that's going to be that, and that. Alright, so that's what they should look like, upper rectangles. Okay, so does it say 3 rectangles? No, it says 4 rectangles from x is 1 to x is 3. Okay. An overestimate's required, so you get a mark just for drawing rectangles on the graph. Part 2, calculate the overestimate. Now the function we have here is e to the x plus 10 take 6e to the minus x. Okay? And we've got these corresponding x values, don't we? 2.5. So, our upper estimate, the area of the upper, I always want you to think about it. Whenever you have to do it, it's like each rectangle has a width of 0.5. So all we're going to do is factorize that 0.5. Alright, we're factorizing that 0.5, and then we're just adding the y values of each rectangle. Okay, so the y value of this rectangle then, of my first rectangle, I'm just taking the x value and putting it into the function. The y value of the first one is e to the 1.5 plus 10 minus 6e to the minus 1.5. Okay, that's the first y value. And then we have the second y value. Alright, so the first y value went 1.5. The second y value is x is 2. So the same thing, but with x is 2. And then with x is 2.5. And then with x is 3. And so what you're typing in your calculator basically is 0.5 plus this, plus this, plus this, plus this. Okay, we want it correct to 4 decimal places, 4 significant figures. So, that's a fair bit to type in. Maybe we use the table method to do it as well. Okay. so let's, even then, because you're adding them all together, like you can go 10, 20, 30, 40, like that part's 40, e to the 1.5 plus e squared. So let's type all that out. E 1.5 plus e squared plus e 2.5 plus e cubed. I'll work it out, guys. Take 6e. Take 6e minus 2. Take 6e minus 2.5. Take 6e minus 3. All right, we've got 40.598. Okay, so to 4 significant figures. 1, 2, 3, 4. Now 4 significant figures or decimal places? Significant figures, okay. So I've written 5 figures, I round the 5th figure, 8 rounds up. So that means the 9 rounds up, so we have 40.60. Alright. Okay, overestimate has been calculated. Okay, so here's where we're bringing back the calculus. Alright, make calculus great. It is e to the x plus 10 take 6e to the minus x. Find f dash dash of x. Okay, so the first derivative, well the derivative of e to the x is just e to the x. Derivative of 10, that disappears. Okay, then we have take 6, so that's going to be take 6. And the derivative of e to the minus x is minus e to the minus x. So the first derivative then is e to the x plus 6e to the minus x. And so the second derivative then is e to the x, and here this will be take 6e to the minus x. Okay. B part 2. The solution to f dash dash of x equals 0 is correct to 3 significant figures is k equals 0.896. Determine the exact value of k. So we want to know what's the value of x that makes it equal to 0 exactly. Okay. So we're bringing in some exponential skills here as well. So we're solving this equation. E to the x, take 6e to the minus x equals 0. So I think the best way to think about it is, let's move the 6e to the x over to the other side. And now we're going to multiply both sides by e to the x. Okay. Now here we have the same base, e to the x times e to the x, so then we're going to add the powers, e to the 2x. It's the same as e to the x squared, right? And over here we have 6, and we've got e to the minus x times e to the x. When we add those powers, we get e to the 0, and any number to the power of 0 is 1. Alright, so we have 6 times 1, which is 6. Perform the natural log of both sides, so I'll write it out. ln e to the 2x equals ln of 6. This gives us 2x is ln of 6. So that means x is half ln of 6. Okay, the exact value of k, or the x value that makes it true, half ln of 6. Okay. Now, this is like such a beautiful question, because now we're bringing in even a little bit of applications of calculus here as well. For what values of x, so I'm looking at B part 3, for what values of x is the second derivative positive? The second derivative positive. So let's think back to applications of calculus, and for the second derivative, that tells us when a function is concave and concave up and concave down. So if the second derivative is positive, that means the function is opening upwards. Okay? For what values is the function opening upwards? Now, we found the second derivative equals 0 here, half ln6, and we're even told what it is for 3 sig-figs. That's 0.896. You can check your right by putting that in your calculator. See that the same. 0.896 is here. Now, the second derivative equals 0, that's a point of inflection. It's changed from being concave down to concave up. It's positive over this interval. The second derivative is positive over this interval. So the answer to part 3 is x is larger than or equal to 0.8 half ln6. They'll accept the 0.896 as well if you didn't get the half ln6. Okay, so all of that, like I'm just tying in a number of things, but the main teachable moment for this question is part C. This is why we put it in. This is important, okay? So we've calculated an overestimate, but it says an underestimate could also be calculated using 4 rectangles. With reference to your answer here, okay, with reference to this, with reference to the fact that it's concave up over that interval, with reference to your answer, explain which estimate, the overestimate or the underestimate, is going to be closer. One of them is going to be closer. They're not exactly the same width apart. So let's focus on this section that we're interested in, between 1 and 3. And over this interval, it's concave up. Okay? So concave up means it has this shape, right? That it's curving upwards. It's opening upwards. And what I'm going to do, I'm just going to take a random point and draw a rectangle around it. Okay? And I'm going to let's take that little snapshot and let's exaggerate what's going on there. I have a square here, and it's curving like this, isn't it? It's curving like that. So the question is the curve closer to the lower estimate or the upper estimate? Which has more error? And the answer is, look at the error involved with the lower estimate. So that's the error with lower compared to the error with the upper. Okay? There is significantly more error in this region than there is in this region, which means our lower estimate, our underestimate, is going to be more accurate. So this is always going to be the case if a function is concave up. If a function is concave up, the lower estimate is more accurate. And then what would we expect if a function is concave down, if it's opening downwards, okay? You expect the same feature. What's it closer to? We can see now we've got more error with the lower estimate. Okay, so the conclusion of this is, if it's concave up, lower estimate is more true. All right, provided we're using the same number of rectangles. If it's concave down, then the upper estimate is closer. Okay, and that's an important feature, and this has popped up in a number of exams in the past. And this is a really good way to communicate it, that the error with the lower estimate is less than the error associated with the upper estimate. Okay, so that's really all I wanted to point out there, is this relationship. Very good. All right, any questions about that question? Okay, so everyone remember how to do the second derivative, and everyone remember concave up and down?